All right, good morning, everyone. Welcome back. So we are going to have two more lectures today. These are going to be the last lectures we have on new materials, and then we're going to have a review for the final exam next Tuesday. And the final exam is scheduled on the 30th from 7:30 to 9:30. Unfortunately, we are not allowed to change that time. I know it's early, but that's the time slot we are putting. I will start the final exam window at 7:30. I will allow the window to expire probably a little beyond 9:30, depending on whether you have. If you don't have another exam following up, then you may have a little bit of extra time to plan for your final exam. So we'll talk about some of the details, specifics of the final exam requirement next Tuesday. So make sure that you don't miss that. And then I'll still have office hours next week and the week after. 30th is Thursday, so we'll have the office hour next 2 weeks from 1 to 3 on Wednesday afternoon, and then the TA will still have his office hour on Mondays. Okay, so this is what we're going to be planning for the remainder of the semester. So that's really close up to the end. And for this semester, obviously, we are doing everything online. And the summer is also going to be online, as the university has previously announced. We don't know yet about the fall. I believe we may be able to get back on campus for the fall, but we don't know. Just look at how things are going in the US in general, and then also in the state of Florida and Alachua County specifically. It looks like things are leveling up to some extent, but actually yesterday, if you guys follow the news, there were almost 5,000 deaths a day yesterday. That was really deadly, obviously. And then, but in the last few days, it was sort of leveling up a little bit, but you know, we see that big spike. We don't know if it's just a single day spike or it's signaling a trend. We don't know. In the state of Florida, it looks like the worst is yet to come based on some of these model simulations, especially looking at this Institute of Health metrics and evaluation from University of Washington. It looks like we may be seeing the peak by around May 1st-ish in the state. So I really cannot predict what's going to happen. Just be smart and protect yourself and folks around you. So in terms of what we are going to cover in this course, so today the two lectures will be about magnetic properties. So let me share the slides with you. All right, so so we're going to talk about the basics of magnetization, and then look at the classification of materials based on their different magnetic properties, and then finally we'll look at superconductors and then the very special magnetic properties. So this is actually somewhat connecting back to the electrical properties of materials we talked about earlier. So to talk about magnetic properties, we have to understand why certain materials have magnetic, they can show these magnetic responses. That starts again from the atomic level. Okay, so we can look at these so-called magnetic dipole moments. So in a way, the magnetic properties, as you're trying to understand the magnetic properties, you can use a lot of these concepts, similar concepts from electrical properties. So we talk about electrical dipoles. Okay, so here we are using the magnetic dipoles as a way to describe how these materials potentially can interact with the magnetic field you apply from the outside. So for these magnetic dipoles, now the cause of the magnetic dipoles is a little bit different from the electrical dipole, obviously. And definition is a bit different as well. But in terms of dipole moment, you have certain magnitude and also direction. Okay, so in this case, for magnetic dipole, it's formed by basically a closed current loop. Okay, a current loop, as if you use the right hand and circle around the current, and then your thumb direction is going to be shown. So you have the current loop, and then you have the thumb pointing. Basically, that's the normal direction of that loop. So the magnetic dipole moment is defined as a current multiplied by the area that the loop encloses, and then the direction is given by the normal direction of that loop. Now, obviously, if you reverse the current direction, then the loop is still the same, just the current runs in the opposite direction. That means the magnitude of the dipole moment will be the same, it's just that the direction of the dipole will be flipped toward the other end, okay? So under a magnetic field, so in materials, we have a lot of these magnetic dipoles. I'll explain what these dipoles are in atoms. But if you put one of those dipoles under a magnetic field, B, the B field, and then the magnetic dipole will see a force exerted by the external field. Well, basically now you have some potential energy associated with that magnetic field. Okay, and so you have a force applied, and then the force will result in the torque, and that torque tends to turn the dipole in a direction that is aligned with the magnetic field. So the torque is mu cross B, and you can also look at the potential energy is minus mu dot B. So this is in a way similar to the potential energy we talked about earlier when we put an electrical dipole inside the electrical field. It's also minus mu dot E. Okay, so the format is somewhat similar, but the idea is that the dipole moment likes to be aligned with the magnetic field completely. Okay, so the dipole will be in the direction of the magnetic field. That will give you the lowest potential energy. If the dipole moment is anti-parallel with the B field, so basically pointing from right to left on this slide, then it'll give you the highest potential energy. Okay, so if the dipole moment is aligned, that means pointing from left to right, same direction as the B field, you have the lowest potential energy. If it's in the opposite direction, it'll be highest anywhere in between. For all other directions, the potential energy will be between the highest and the lowest point. Excuse me. So that will basically allows the dipole to be aligned with the magnetic field, in the sense that this is similar to the dipolar or the orientational polarization mechanism. As we were talking about, we have a permanent dipole, you have an electric field, then the dipoles like to will preferentially align with the E field. Okay, now we'll come back to this alignment issue a bit later as we look at the dipole responses. But obviously for magnets, we know that north and north, if you have two different magnets, the north ends will repel each other, the south ends will repel each other. One north and one south, they can attract each other. Okay, and you can also define these magnetic field lines as going out from the North Pole through the open space and get back into the magnet through the South Pole. Okay, so it's sort of, you can use that. The current, if you have a current loop, then the current loop will be looped around all these magnetic field lines. These field lines actually are going to go in and out of the loop area. Okay, and then the direction of the dipole moment is basically the North Pole direction going out. Okay, so these magnetic dipoles, they generate that magnetic field. These are the field lines that's being generated. So inside these atoms, we can have two different kinds of magnetic dipoles. One comes from the orbital motion of the electrons around the nucleus. So for example, in this case, if we have electron moving, basically looks like it's clockwise, then the current, since electrons carry negative charge, the current will be in opposite direction. So the current will be counterclockwise. So counterclockwise, if you move it, then the orbital magnetic dipole moment will be pointing in the upward direction. And then if you have the electrons moving sort of clockwise, then the angular momentum is pointing downward direction. Okay, so for the electrons, you can actually, this is, maybe you have seen this in physics too. If not, we have this relationship shown here. The orbital magnetic dipole moment scales with the angular momentum of the electron, and the proportionality constant is negative minus E over 2m. And this is, they call it gyro, or just remove the negative sign, that E over 2m is called gyromagnetic ratio. It links between the angular momentum, which is r cross p, p is the linear momentum mv, to the orbital magnetic moment. Okay, so that means that when we have some electron motion to form a circle, so you have, this is somewhat sort of classical picture of a orbital. Okay, then you have a current, and the current will generate a magnetic dipole moment. But there's also the spin motion. A spin has an angular momentum as well, capital S, and then you can also define the spin magnetic moment in associated with the spin angular momentum, and then but the gyro magnetic ratio is a bit different. It's E over m, not E over 2m. I'm not going to get into the details about the difference, but just take that as is. And then when you look at the total atomic magnetic moment, you have to sum up both the orbital motion and the spin. For atoms, obviously, each atom may have certain electrons, and then you have to just add up all the orbital and spin components for all the electrons to get to the total atomic momentum, magnetic momentum. Now, that's more or less a classical picture, but we know that we've learned quantum mechanics, so we know that the spin angular momentum and also the orbital angular momentum, all of those things are quantized. Okay, for spin, we have the spin quantum number being 1/2. So the projection around a potential B field, any direction. So let's say now we take this Z direction as the direction of the applied B field magnetic field. Then the projection of that spin angular momentum in that Z direction will be quantized as well, and that SZ will be either +1/2 or -1/2. That means if you look at the spin magnetic dipole moment, its projection around the B field, mu Z, will also be quantized, because mu Z is going to be minus E over m times SZ. And if SZ, the Z component of the spin angular momentum, is quantized, being 1/2 h bar or -1/2 h bar, then correspondingly this mu Z will be quantized as well, to be minus plus E h bar over 2m. And then we actually define this E h bar over 2m, call it Bohr magneton. So this is actually, you can think of that as sort of a measurement unit for the atomic magnetic dipole moment. Okay, so for electron spin, if you plug in the numbers, and you will see that the mu Z is plus minus mu B. So it's either one Bohr magneton pointing in the direction of B field, or -1 Bohr magneton pointing in the opposite direction of the B field. Okay. For the atomic motion, we know that these orbitals will have these quantum numbers n, l, m. Okay, we previously explained what n is. It's a principal quantum number. And l is the angular momentum quantum number. So if you have the L squared, the angular momentum operator, then the corresponding value will be related to L. It's L times L plus 1 times h bar squared. But now we are understanding what the meaning is for m sub L. Okay, this m. Okay, at that time we called it magnetic quantum number, but we didn't really talk about why it is called that way. Okay, we only say that its value can be from anywhere from -L plus all the way to plus L with difference of 1. All these integers between -L and plus L. Okay, but now as we've talked about the magnetic dipole moment, looking at the orbital contribution, it's minus E over 2m times the angular momentum for the orbital motion. So in that case, well, just think about this as being L, and then you have corresponding LZ, right? So if you have LZ, then corresponding mu Z is going to be quantized as well. Okay. So previously we said LZ has been quantized, and its value is ml times h bar. So now you basically have this mu Z being quantized as well. Okay. And then just remind you that L, the total length of the angular momentum for the orbital motion is quantized, having this value. So, so in this case, the reason that we call this magnetic quantum number is that if you think about placing these magnetic dipole, these orbital, magnetic dipole moment only inside this magnetic field. Remember, as in the previous slide, we talked about there is going to be a potential energy associated with that dipole moment, magnetic dipole moment in the magnetic field. So, and the result is basically mu z times b, or there's a negative sign in front of it. So it shows you that once you have a magnetic field, then all these N, L, M, L states are going to have different energies. Previously, we said without the magnetic field, the energy will depend on both N and L. That's for without magnetic field. With magnetic field, now you see that because of this minus mu dot B potential energy for the magnetic dipole in the magnetic field, the energy will depend on how much this ML is, because mu Z, as you see here, mu Z is minus E over 2me times ML times H bar. So if you have different ML, minus L versus plus L, then that potential energy for that magnetic dipole moment in the magnetic field will be different, and that will cause the overall energy of this quantum state to be different for different MLs. Okay, so that's why we call this M sub L magnetic quantum number. Okay, so now there are a couple more things. This is for one single electron. If we do have a closed subshell, let's say the S state, S orbital is filled. Then if the S orbital is filled, the S orbital has L being 0, so it doesn't have the orbital contribution to the magnetic dipole. For the electron spin, well, if you have two electrons in the S orbital, one has a plus 1/2 ms quantum number, and then the other one has minus 1/2, then the mu z will be in opposite direction for these two electrons. And so if you look at the entire atom, then these two will cancel out. So if you have a closed subshell for the s orbitals, as we explained, the total magnetic moment of an atom will be 0. Okay. Now, what if you have a L orbital? P orbital. P orbital will have L being 1, so now you have a capital L being non-zero. But again, in this case, you're going to have ML going from -1, 0, and +1. So you have these three different substates, quantum states, all filled with electrons. Each orbital will have electron with positive spin and negative spin. So the spin contribution, again, well, as soon as these two electrons are paired, then their contribution to the spin magnetic dipole moment will be cancelled. If all these different p states are filled as well for different m's, -1, 0, and +1. Again, -1 and +1, looking at their LZs, one's going to be h bar, the other is going to be minus h bar. So correspondingly, their mu z will take opposite signs with equal magnitude. So again, if you sum up all these different states, their contribution to the orbital magnetic dipole moment will cancel out as well. So overall, for all the electrons, for any closed subshells, so that's it, s orbital, you're going to have 2 electrons. P orbitals, you're going to have 6 electrons. D orbital, you're going to have 10 electrons. Or F orbital, you're going to have 14. If all those orbitals are filled, all these states are filled in for the same subshell, then the contribution from all those electrons to the magnetic dipole moment is going to be 0. So only these unfilled subshells will have some non-zero magnetic dipole moment. Things like, let's say, in copper, for example, copper 3d10, 4s1. Then 3d electrons, you have all 10 electrons filling all 10 potential quantum states in the d orbital. Then d electrons do not have any contribution to the magnetic dipole moment. The 4s1, it's not paired in the 4s orbital, then it will give you some non-zero magnetic dipole moment. All right, so that's from the atomic level. Now let's look at the materials level, the macroscopic level, and see how we can describe the overall magnetic properties of materials. And for that, we have to introduce this magnetization vector. This is in a way similar to the polarization vector that we talked about for electrical dipoles. So for magnetization, let's first look at a very long solenoid, basically a coil. Okay, a coil, so you can have many turns, and then you run the current. Then obviously the current in any turn will be the same. let's say it covers certain length, and then with some, let's say inside we have some free space first, and the magnetic field is B0. And this B0, the strength of this B0, the magnetic field, is related to how strong the current is and also how many turns we have per unit length. Okay, so B0, following physics 2, it can be described as mu0 times n times I. This mu0 is the absolute permeability of the free space. This is a physical constant. Okay, and this n is number of turns per unit length, and this I prime is basically n times I. So basically, if let's say per unit length you have 3 turns, then it's 3 times the current. So basically, you have to add up all these currents. Okay, so this I prime is current per unit length. Now, if we do put a certain material inside the solenoid, okay, then this material may develop some magnetization. Okay, and this magnetization is similar to the definition of the polarization vector. Polarization vector is the total electrical dipole moments per unit volume, and here magnetization is defined as the total magnetic dipole moment per unit volume. So it's also the if you have the average dipole moment per atom, then you also have the atomic concentration, then it's a product of these two. Now, obviously, as we talk about for electric dipoles, you have these 2 charges physically separated. For magnetic dipoles, we basically have current loops. Okay, so we can kind of consider that we have many these little current loops inside, and these little current loops, if you look at the overall effect, basically there's a surface current loop. This is similar to the magnetization, the electrical dipolarization in materials. When we talk about these materials have these individual electrical dipole moments, but inside, basically you average things out. You only leave charges on left side versus right side of the surfaces. So things are similar here. For magnetization, these little current loops inside, they cancel out, so you only leave some surface current loop. Okay, and this current loop for a cylinder with a certain area and length, the total magnetic moment for this will be this magnetization times that volume. Okay, remember magnetization is the total dipole moment per unit volume. So if we have this volume A times L, that's a cylinder, then multiplied by the magnetization, we get to the total magnetic moment inside this entire volume, this material. And if you treat that as a big magnetic dipole, then it'll have a certain surface current multiplied by the length. Okay, and so you can kind of consider that we have some sort of a magnetization current on the surface. And if it's per unit length, then it'll just be Im times the this L. This is a current times the area that gets you the dipole moment. Okay, so essentially this surface current loop, the current inside this surface loop is the same as a magnetization. This is somewhat similar to what we talked about earlier. For the electrical polarization, if we look at the electric field, it's just the P actually divided by epsilon 0 at that point. Okay, but here the magnetization vector is related to the surface magnetization current. Okay. All right. So now, how does that apply to actual materials? Okay, or sort of the magnetic responses. So you need to look at magnetic permeability. Remember, mu0. That's the absolute permeability in the free space. So that's for free space. Okay, so that's physical constant. And then for a specific material, its magnetic permeability may be a certain number times the free space permeability. It's sort of similar to the electrical dipole polarization, the dielectric constant, which is the relative permittivity. Okay, so the absolute permittivity is the relative permittivity or the dielectric constant multiplied by the vacuum permittivity. We are trying to find a similar relationship here, trying to find some unitless numbers to describe the relative permeability of materials that's to characterize their magnetic responses. Okay, so in this case, the actual magnetic field, the actual B field inside the material will have two components. One is the magnetic field caused by the previous current loop. You can kind of consider that as the external magnetic field applied onto the material that we have inside. Okay, and then because we have a surface current loop, magnetization current loop on the surface of this material, that also give you some additional magnetic field inside as well. So the total current is just the external current plus the surface current, and then multiplied by mu0. That gets you the actual B field we have now. And mu0 times I prime, that's just the original external B field. And this mu0 m, m is the magnetization that we just talked about in the previous slide. So in this case, now you can obtain this B field inside the material now being the sum of the two components. One is the external B field, and also the B field contributed by the magnetization inside this material. Okay, so this there's also, as you guys, if you guys remember, there's also the H field. Okay, this is so-called magnetizing field or magnetic field strength or magnetic field intensity. It's got different names, but easiest way to say this is the H field, not the B field. Either of them can be used to describe the magnetic field, but B is typically called a magnetic field, and then the H is called magnetizing field. It's a little bit sort of awkward in terms of this distinguishing between these two quantities. So simply saying B field, H field, okay, and the H field is defined as basically. The H field does not depend on the material. Okay, so basically you take out the influence of the material, that basically is the B0 divided by mu0, that gets you to the H field. So H field is the same. And so with that, it's basically dictated by the current loop that you have on the outside of the material. This is the current inside the solenoid, inside the core. Okay, so now we can define the magnetic permeability. So H field is sort of the constant, okay? So now if we have a specific B field inside the materials, then the B field divided by the H field, we get to the magnetic permeability. And it can be expressed as a product between the vacuum permeability multiplied by some relative permeability. And this relative permeability is sort of, this is in comparison to the relative permittivity for the electrical polarization. Okay, so basically now you have this relative permeability being basically the actual B field we have now, the ratio of that to the original B field, the external B field. Okay, you can also define the magnetic susceptibility being basically magnetization over the H field, and then you can draw that this mu r, the magnetic permeability, is just 1 plus the magnetic susceptibility. And remember, for the electrical properties, dielectric property, we know that the dielectric constant epsilon r, the relative permittivity, is 1 plus chi e. Well, now since we have different susceptibility, the previous susceptibility, we're going to add a subscript e. So overall, it's sort of similar. Magnetic properties, they have this relative permeability being 1 plus the susceptibility, the magnetic susceptibility. For the relative permittivity, the dielectric behavior, epsilon r is 1 plus chi e. So it's a sort of similar, and then it's relating basically three terms here: B field, H field, and the magnetization. In the case of electrical dipoles, we have the E field, we have polarization. There's also so-called D field displacement, but that's sort of similar here. Okay. All right. So we talk a lot of the different terms associated with the magnetic behavior, or how we sort of characterize the magnetic properties, and there are many different sort of B field. And associated with that, we have the flux, dipole moment, and the Bohr magneton, E h bar over 2m. You can kind of consider that as a constant as well, because E is constant, H bar is constant, M E obviously that's a constant. So you can go from all these physical constants to obtain the Bohr magneton, but obviously that's a fixed number. And then you have the magnetization vector, the magnetizing field, and then the magnetic susceptibility. We have the absolute permittivity, permeability. This is the vacuum permeability. It should be the absolute permeability in vacuum. Okay, so we have the relative permeability, and then the magnetic permeability is the product of mu0 and mu r. Okay, so take a few seconds just to go through this list of different kind of terms, and then see how they are related to each other, and then the units. So the reason we are learning all these, some of that, hopefully you've learned that in physics too, but it's probably a while. So it's probably time to refresh some of that. But ultimately, we want to apply these concepts to understand how materials may be classified based on their different magnetic properties. If you were given a particular material, what kind of magnetic responses can they have? Okay, so there are different kinds of responses. One, the first thing we are going to talk about is called diamagnetism. Okay, dia basically sort of going against the magnetic field. All right, so here we have the relationship between the magnetic field we have in the material being having these two terms. One is the external B field, and also the magnetic response, the magnetization. Okay. And then we know B0 is mu0 times H. So, and this chi M over H is the magnetic susceptibility. And then we have the relative permeability being 1 plus the susceptibility. And that's just the B field we have in the material over the B field that's applied by the external current loop. So in the case of diamagnetism, the characteristics is that the magnetic susceptibility is negative and also small. Okay, well, so in general, it says for the diamagnetism, if the magnetization is in the opposite direction of the H field. Okay, so the M is in the opposite direction of the H field. That means we have a diamagnetism. Okay, so this is sort of the general requirement for diamagnetism. The susceptibility is negative. So actually the magnetic field we have in some material is actually less than the magnetic field applied previously. So in the case of electrical polarization, that's mostly always the case. The actual E field inside the material is less than the E field you apply from the outside. That's just because the electrons or the other kind of charges will respond to the external electric field in a way that it'll develop a polarization that is in the opposite direction of well, it's in the same direction of the E field, but the corresponding depolarizing field tends to cancel out the external E field. Okay, but in this case, for magnetic responses, diamagnetism is just one kind of response. And so this diamagnetic material basically says that the material will be positioning itself so that the actual B field will be less than the applied E field. So in a way, you can kind of consider that, well, you have this magnetic field being generated from the external source, and these are the magnetic field lines. And then obviously, as you move it further away, it'll tend to sort of lower the magnetic field. Okay, so that's kind of the response you can envision. Okay, so if you have a diamagnetic material placed in a non-uniform magnetic field, it'll basically experience a force that pulls it away from the magnetic source, and then it'll tend to lower the field. Okay. And also remember that the magnetization is in opposite direction of the B field. The B field points from left to right, and the H field also points from left to right, but the magnetization is going to be in the opposite direction. Okay. Now, many materials do exhibit diamagnetism, and it's these materials that do have closed subshells. Basically, there's no permanent magnetic dipole moment. Okay, so in that case, the diamagnetism is a general response. Now, for these materials, actually, the magnetic responses is very, very small. Okay, you see here, it's negative for sure. Okay, so that's a feature of diamagnetism. Okay, But at the same time, that chi-m, well, remember chi-m and also mu r, both of them are unitless numbers. 2, 3, 4, 7. That's what we have learned from the dielectric constant, the relative permittivity. For the relative permeability, it's relative. So it's also unitless, okay? Same with chi-m. But now you see the chi-m here is a very, very small number, 10 to the minus 6. That's it. That's basically says that this mu r is essentially 1. That means for all practical reasons, if we are looking at this, the actual mu, the magnetic permeability, it's essentially the same as a vacuum permeability. The magnetic response is so negligible that we can basically neglect that for these materials. Okay. Now there is one kind of exception that is called superconductors, which we'll talk about in the next period. For the superconductors, it'll completely repel the magnetic field. So that means that the actual magnetic field, B field inside the material will be 0. If the B field is 0, it means that this H and M will be will have the equal value, equal magnitude, but in opposite direction. So that's M over H bar is exactly -1. So it's negative, so that's diamagnetism, but it's going to be -1 to give you a mu r of 0. Okay, so that's a very special exception. In general, when we say diamagnetism for a material, for a typical material, the chi is going to be a negative number and it's very small. But only for these superconductors, when they expose the diamagnetism, it can actually completely remove the external B field so that the B field is inside of 0. All right, so that these are the materials with other than superconductors, materials with closed subshells or materials with no permanent magnetic moments will exhibit diamagnetism. What if a material has a permanent dipole? Then these permanent dipoles are very similar to the electric dipoles. So they may preferentially align in the direction of the applied E field. Now, in this case, magnetic dipoles may preferentially align with the applied H field, and then cause a partial alignment of the dipoles in the direction of the H field that give you like in the case of electric dipoles, it give you a average induced dipole moment in the direction of the E field. In this case, it's similar. If you don't have the E field, H field, then these magnetic dipoles, the permanent dipoles, may randomly orient, get you a 0 total magnetization for the material. Once you apply the external B field or H field, then these magnetic dipoles may preferentially orient. Again, you have to look at the potential energy caused by the external field onto these dipole moments, and then you follow the Boltzmann distribution. So it's more likely to have these dipole moments align or in the direction parallel with the H field than in the direction anti-parallel, in the opposite direction. Okay, so that gets you an average magnetization, magnetic dipole moment in the direction of the H field that give you a non-zero magnetization for the material. Okay, so this is so-called paramagnetism. So if you have M and H in the same direction, then the ratio is going to be a positive value. Okay, so that gives you a positive chi-m. But again, this chi-m is small. Okay, so you have a typical number, let's say oxygen gas. And that number is positive, but it's still only order of 10 to the minus 6. Now you may ask, oxygen is O2, right? So O2, because of the covalent bonds, apparently you have closed subshells for both atoms. That's the classical way of looking at the bonding, but looking at the quantum side, it's actually a little bit different. So this is an experiment to demonstrate the paramagnetism of oxygen molecules. So you have a duo, you pour out liquid oxygen, and you actually see that the oxygen molecule will be attracted toward the magnets. So remember previously when we said diamagnetism, they will try to be repelled to push the material into a lower magnetic field range. But here now you're pulling it in, so that's a paramagnetism, it's an opposite motion. So you have to look at the atomic orbitals of oxygen atoms and then see how the molecular orbitals can can be formed. So that's the atomic orbital. You have 2s2 and 2p4. So 2p4 means that you have one pair and then two unpaired electrons in the p orbitals. Okay, same thing with the other oxygen atom. And once they form the orbitals for the 2s, you'll form a bonding orbital, molecular orbital, and the anti-bonding molecular orbital. Now, since both 2s orbitals are already filled, so you have 4 electrons. That's why both the bonding and the anti-bonding molecular orbitals will be filled. For the p orbitals, you start with the if you put 2 oxygen together, you have the sigma bond, okay, and you also have the pi bonds. Okay, pi bonds are the side by side. Okay, so the s bond, if you think about the s orbitals, they're head to head, but then you have 2 perpendicular directions, and then these orbitals, p orbitals, the unpaired orbitals will form these pi bonds. Okay, in the 2 perpendicular directions. That's why we have the sigma bond bonding orbital and the anti-bonding orbital, and the pi bond bonding orbital and the anti-bonding orbital. Now the pi bond has less energy separation because that pi bond is not as strong as the sigma bond. So the separation between the bonding and anti-bonding sigma orbitals will be greater than the separation between the bonding and anti-bonding pi orbitals. Okay, so with that, you have 2 pi orbitals, 1 sigma orbital, and then you have the corresponding number of anti-bonding orbitals. Now you have 4 electrons from either side, so that's you have 8. So now you're trying to fill all those 8 electrons into these orbitals. So you are going to fill these bonding orbitals. That's 6 electrons. You have 2 more that will put you into these 2 pi anti-bonding orbitals. And since we have 2 of them, you have 2 electrons. You want to maximize the distribution, so you actually align these spins and then put them into separate orbitals. This is the same as the Hans rule that we talked about earlier for atomic orbitals. And like we have these two electrons in separate pz orbitals, p orbitals, but each of them is unpaired. So now in this case, you said we have 2 unpaired electrons in the molecular orbital. So these unpaired electrons, each one of them gives you 1 Bohr magneton magnetic dipole moment, so 2 of them will give you 2 Bohr magneton. Okay, so that's why overall these oxygen molecule will show paramagnetism. Okay, that's one kind of paramagnetism you can have. The other type of paramagnetism is seen in many of these metals, like a magnesium. Chi-M is slightly higher, 10 to minus 5, but still in the general schemes of all things, it's a very small number. Mu R is essentially still 1. Say it's a very minor correction from the vacuum permeability. I'm sorry. So now the compared to the oxygen gas, it's bigger, but overall it's still small, and that's called a polyspin paramagnetism. It's all because of the valence electrons. Okay, and this is explained here. The polyspin paramagnetism in metals is due to the conduction electrons. Each electron, as I mentioned, carries spin-related magnetic dipole moment plus minus Bohr magneton. Okay, and so we can look at the density of states. If you guys still remember that concept, the density of states for free electrons, we have this density of states go by e to the 1/2. So this is a minimal energy, and then it's go up, and then at some point we have Fermi energy. All the states below the Fermi energy will be filled with electrons. States above Fermi energy will not be filled, and then it has this sort of parabolic shape. The density of states go by square root E. Okay, but at that point we didn't really identify the spins. We only said a spin for each atomic, for each orbital quantum state, a spatial quantum state. We can have 2 electrons in it, 1 spin up, 1 spin down. But now let's split the spins. So we have half of the states, actual quantum states, will spin up. The other half has spin down, and then obviously we spin up, spin down. If we don't have a magnetic field, then the energies are the same. But once we have the energy, once we have the magnetic field, then the spin, different direction of the spin will give you different magnetic dipole moment, and that magnetic dipole moment, once you place that in the magnetic field, they will give you different potential energies. Okay, so with that, you're going to have a spin, sort of the degeneracy will be split degeneracy means that spin degeneracy means that different spins have the same energy. But once we have the magnetic field, the different spins will give you different energies. So that will destroy that spin degeneracy. So essentially, in this case, if the B field is pointing upward, that's in that direction, then for the spins in the same direction as the B field, the magnetic field is going to give you a negative potential energy. If the dipole moment is pointing in the opposite direction as the magnetic field, then the magnetic field is going to give you a positive potential energy. So the energy on the left side will be raised with respect to the right side. And in the end, we want to maintain a constant Fermi energy throughout the system. So the electrons here, we have to move to the electron to fill the electronic space on the other side. The final result is that now we have more electrons will spin up than electrons will spin down. So the total net result is that we're going to have, as a whole, previously we have spin cancellation, magnetic dipole cancellation, but now the magnetic dipole moment from electrons with positive spin is going to be greater than the magnetic dipole moments coming from all these electrons with spin pointing downward. So we're going to have a negative, or we're going to have a net dipole moment, magnetic dipole moment from all these electrons. And that's in the same direction that generates this overall magnetization vector, and it's in the same direction as applied B field. So that gets you a paramagnetism. Okay, it's all about the redistribution of the electrons after they see this additional potential energy. That's different for the dipole moments pointing in different directions. Okay, so this magnetization is in the same direction as a magnetic field. That gets you a positive susceptibility, magnetic susceptibility, and that gets you the overall relative permeability being slightly greater than 1. Okay, very slightly. Okay, now there are materials with the susceptibility very large, or the magnetic dipole moments very large. By the way, between diamagnetism and paramagnetism, it probably encompasses the majority of the materials that you may be facing with. So there are specific materials called ferromagnetic or antiferromagnetic or ferrimagnetic materials. This is a very relatively small class of material. In terms of number, it's very few, but they have very, very important use in everyday life, or in scientific research. So let's first look at the ferromagnetic material. So essentially, we have these permanent dipoles. These are the magnetic dipoles. Okay, for each individual atom, it may be somewhat significant. Okay, and for whatever reason, they are all aligned in the same direction. Okay, so this is similar to the ferroelectric material, when we have this so-called spontaneous alignment of these electrical dipoles. So in the case of magnetic materials, if all these magnetic dipole moments are aligned in the same direction, that we call this a ferromagnetic material. Okay, so it's the parallel alignment of all individual magnetic dipoles, and all of them have the same magnitude. Now, if some of them are turned in the opposite direction, such that we have equal number of dipole moments pointing in opposite directions, then if they have the same magnitude and they have the same number, then overall magnetization will be 0. This is so-called anti-ferromagnetic material. Okay, they're all anti-parallel. Well, obviously not all, but we have equal number of anti-parallel dipole moments, and they are the same. Now, if the anti-parallel alignment is still there, but unfortunately the magnitude of these dipoles are not the same, then we have so-called ferrimagnetic materials. And we have opposite alignment, so alternating arrangement of dipole moments pointing in opposite direction, but they are not completely the same in magnitude, so they are not going to cancel out each other completely. So essentially, if you look at the overall magnetization, it's still somewhat similar to the ferromagnetic, but you do have the anti-parallel alignment that's similar to the anti-ferro. So it's sort of a combination of these two that gets you to the ferrimagnetic alignment. So in all cases, we have the so-called magnetic ordering. This ordering in the ferromagnetic is all parallel with each other. In the antiferro or the ferri, that we have the alternating arrangement of anti-parallel alignment. Okay, so whatever way, these are different order structures, but they have the magnetic ordering. And this magnetic ordering may be on top of the typical crystal ordering that we have. Remember, in crystals, we have unit cells, and so in that case, we have crystal ordering, but this magnetic ordering may be a different layer of ordering on top of that, okay? And both the ferro and ferri magnetic materials may possess some high spontaneous magnetization, even in the absence of magnetic field, okay? But obviously, there's also a potential limitation, that is, if the temperature is really, really high, then the random motion may actually destroy that. So basically, there's a Curie temperature or Néel temperature for the ferromagnetic materials. Then, in that case, the ordering will be lost. So they're not locked in anymore. In that case, they'll become paramagnetic. So this is just, before we get to a break, I'll just show this table of sort of comparing all these different kind of magnetic responses. Dia, para, in general, these materials have relatively small susceptibility. For dia, it's going to be negative. Para, it's going to be positive. And they are mostly temperature independent for the susceptibility. For the diamagnetic, there's also a special case when the chi-m is exactly -1. These are superconductors. And then for these ferro, antiferro, or ferri, they do have magnetic ordering. In both cases, in all these cases, the susceptibility will be positive. For ferro and ferri, the chi-m will be very large, but obviously that's going to be below certain limits, below the Curie temperature limit. Okay, for antiferro, they can have some positive chi-m, but because the alignment is locked in the antiparallel direction, that the chi-m will be small. It's also has to be below certain Néel temperature. So once you have these materials above the Curie or Néel temperature, then their ordering will disappear. So they actually will convert back to these paramagnetic behavior. In that case, you still have positive chi-m, but the value of chi-m will be small. They have some temperature dependence governed by this Curie or Curie-Weiss laws, which we're not going to get into the details, but just the general behavior. And then some of these materials lists are shown here. These magnetic materials like iron, cobalt, nickel, these are the magnets. And then some of these oxides or fluorides may have the antiferro magnet responses, and then you have some ferrites show the ferrimagnetic responses. Okay, so we went over a little bit longer, but let's take a 3-minute break, and then we'll come back and try to finish up the rest of the slides here. Thank you.